Hello and welcome back to the final session of this short course. We are just going to do review here. There's not going to be any new material introduced. And the format will be as follows. We'll have a question slide with some questions on it, followed by an answer slide. So you may want to pause on the question slide for a minute and try to answer the questions yourself before hearing them in the next slide. We're going to try to combine concepts here, which is necessary to develop a good understanding. So the material may not necessarily be in the exact order that it was covered. In question slide 1 here, we'll take a look at function definitions. We often see definitions like the two shown on the slide. So what do these mean? What are F1 and F2 shown here? What is on each side of the arrow? What are the supersets of F1 and F2? Are these relations? So the first three questions are related to the two function definitions shown. Also, we have two more questions. What is the superset of the less than operation? And what is the superset of the function y equals x squared? So when you answer these questions, think back of the definition we used for functions. Okay, moving on to the answers of slide 1, function definitions. So both F1 and F2 were function definitions. And remember, functions in the set theory definition that we used are subsets of the Cartesian product of the domain with the codomain. The domain being the set on the left side of the arrow and the codomain being the set on the right side of the arrow. So F1 was a function definition. We don't know the rule of the function, but we know that the function maps from 2D positions in R2 to single-valued outputs in R. So the function, the entire function, is a subset of R2 times R is R cubed. So our function is a subset of triples that are elements of R cubed, given that f of xy equals z. In our second function definition, very similar, our inputs are 2D inputs. Now we are explicitly writing the set of all inputs given. So instead of writing, say, b squared, we're actually giving a subset of b squared that are the inputs of the function. Other than that, there's really no difference. We are giving an input set on the left, which is that set of two ordered pairs. So the function f2 is a subset of that set of two ordered input pairs and the Boolean domain output. We don't know what the function is because we don't know the outputs. But we know that we are mapping from that specific set of inputs, which only has two options, to a single output in the Boolean domain. Now, functions are indeed relations. They always are. Remember, a function is always a special case of a relation, just with the additional rule that it has to be an n-to-1 mapping. The superset now, moving on to questions 4 and 5, which were not related to the function definitions that we wrote. The superset of the less than operation on R, remember this is a relation. This is not a function, and we are relating an input element to an output element, each in the domain of the real numbers. So the superset of the less than relation is a set of ordered pairs found in R squared. So the tuples in this case are pairs. The function x squared or y equals x squared maps one input to one output, so it maps one input x to an output y. Both, let's say, are also in the real numbers, so the superset of the function y equals x squared is also r squared, or the square or Cartesian product of the real numbers with itself. Moving on to our second question slide, and this is a series of questions on sets. Question 1, is the Boolean domain a subset of the real numbers? What is the cardinality of the Boolean domain? That's our second question here. 3, given that the unary not operation, or the not operation on the Boolean domain is a unary operation, what is the cardinality of the unary operation not? For the same logical not, what is the cardinality of its superset? What is the Cartesian product? This is question 5 now. What is the Cartesian product of the set with the two elements 1 and 2 with the set with the element A in it? Question 6, what is the cardinality of the logical AND operation, and what is the cardinality of its superset? What is the set with set builder notation here? Open bracket, x is an element of the natural numbers given that x squared equals x. And remember, the vertical bars indicate the cardinality operation. You may want to pause here for a second before moving on to the answer slide. Moving on to the answers to the set questions. Is the Boolean domain a subset of the real numbers? Yes, it is. Remember, the Boolean domain was a subset of the natural numbers, which in turn is a subset of the whole numbers, in turn a subset of the rational numbers, which in turn is a subset of the real numbers. So both of the numbers in the Boolean domain, the numbers 0 and 1, are also found inside the set of real numbers. What is the cardinality of the Boolean domain? Remember, it's a measure of the number of elements in the set. The Boolean domain only has 2 elements in it, so its cardinality is 2. Moving on to the third question. Given that the logical not operation is a unary operation on the Boolean domain, what is its cardinality? There are 2 ordered pairs in this mapping. There are 2 possible inputs in the Boolean domain, each mapping to 1 output by our n-to-1 function definition. So there are just 2 ordered pairs in this entire mapping. So this set of 2 ordered pairs fully describes the unary not operation. So its cardinality is 2. You see the number 0 maps to the number 1, and the number 1 maps to the number 0. The 2 ordered pairs fully describe this function. So its cardinality is 2. On question 4, for the same unary not operation, logical not operation, what's the cardinality of its superset? So the superset is the set of all possible ordered pairs of a single input and a single output. So that's the Cartesian product of the Boolean domain with itself. So the superset cardinality is 4. So every function is, on the Boolean domain, every unary function is a subset of the Cartesian product b squared. What is the Cartesian product of the set with the numbers 1 and 2 times the set with the single element A in it? That's simple. The answer is just the 2 ordered pairs shown here. So 1, comma A, 2, comma A. Now, what is the cardinality of the AND operation? This is similar in spirit to the unary question that we asked before, but in this case we have a binary operation on B. So we have 4 possible inputs. So the cardinality of the AND operation is 4. There's 1 ordered pair for each input, corresponding to each input. And the length of the superset is the triple product of B, the cardinality of the triple product of B, which is 8. Then we asked in question 7, what is the set given with the set builder notation shown? So here we have the set of numbers in N that equal their squares. There's only 2 numbers in N that equal their squares. This is actually called idempotence. We'll see that later, but in a later course. But the 2 numbers here are 0 and 1, and it happens to be the Boolean domain. So this particular set builder notation is a way to describe the Boolean domain. And remember, when you do cardinality, the cardinality of the product of two sets is the product of the cardinalities. In our third question slide here, we have a few questions on the universal set and complement. First question, if the superset is the Boolean domain, what is the complement set of the set with a single element 1, the number 1 in it? So what is the complement of the set with the single element 1? And what is the complement of the set with a single element 0 in it? 2, write out the set definition of the logical NOT operation. So you've already seen this somewhere. The third question, what is the difference between negation and complement? And in this case, consider the negation or the unary NOT operation on the Boolean domain. And in question 4, the same question, what is the difference between negation and complement? In this case, consider negation on the real numbers, or the negative of a real number. And consider the complement also, and compare the two. The answers to our universal set and complement questions are in this slide. So if our superset is the Boolean domain, then the complement set of the set with just the element 1 in it is the set with the element 0. Remember, the complement set is the set of elements in the superset that are not in the set we are taking the complement of. The superset here has the numbers 0 and 1. So if our original set had the number 1 in it, the elements in the superset that are not 1 are just the element 0. The result here is a set, right? And similarly for the complement set of the set with just a 0 element is the set with the 1 element. And these are singleton sets, meaning they just have 1 element in them. Our second question, write out the set definition of the unary logical NOT operation. We already saw this in a previous question, so there are just 2 ordered pairs in this function, and that is the pair 0 and 1, 0, comma 1, and the pair 1, comma 0. So 0 maps to 1, 1 maps to 0. Those 2 ordered pairs are the complete function definition of the logical NOT operation. Now, the last 2 questions are comparing negation with the complement. Negation on the Boolean domain, if we take not 1, we get the number 0, and not 0 equals 1. Looks very similar to the complement, right? Except that our result is not a set in this case. So we're just negating an element, and by the rule of the function, getting another element back. Now, those elements in case of negation on B, or the NOT operation on the Boolean domain, do correspond to that element that we got in the complement set. Now let's look at the same thing on the real numbers. If we negate the number 1, we get another element, minus 1. Right? So we applied the negation operation, unary negation, on the real numbers. So minus the negative of the number 1 is the number minus 1. What about the complement set of the number 1 on the real numbers? So remember, that's all the elements in the superset that are not equal to the set we're taking a complement of, in this case just the singleton or the element 1. That leaves all the elements in the real numbers that are not 1. So if we picture the real line, we would see just a line with all the numbers and a hole at where the 1 is. So it's not exactly the same, right? And if you're interested in this, so negation and complement on the Boolean domain give very similar results. Well, that's not exactly the case on the real numbers. If you want to think about this some more, take a look at 2's complement and how that works. But for here, this is as far as we'll need to go on it. Okay, moving on to some questions about relations, functions, and operations. First, what is the difference between a function and an operation? And question 2, what is the difference between a function and a relation? 3, is the following set a function or a relation? The set of ordered pairs shown. 4, same question for a different set of ordered pairs. 5, write out the entire set that is the relation less than or equal to on the Boolean domain. And question 6, what n-ary operation, or I'm sorry, what n-ary relation is the binary operation plus? And you can pause here for a second if you like before moving on to the answer slide. So question 1, what's the difference between a function and an operation? So an operation is a special type of function, a function that is, it's called closed on a particular set. That means that it's defined for all elements in that set. So a function is an operation is a special type of function. And question 2, what's the difference between a function and a relation? Remember, a function is a special type of relation. So an operation is a special type of function. A function is a special type of relation. A function is always a relation. It's a relation where the mapping has to be n to 1. It may also be 1 to 1, but it cannot be 1 to many. So we can have multiple input elements mapping to one output, or we can have one input mapping to one output, but we cannot have multiple one input mapping to multiple outputs. So, and that sort of answers questions 3 and 4. 3 is the following set of ordered pairs a function or a relation? This qualifies as a function because we have 0 mapping to 1, 1 mapping to 1, so that's 2 to 1. That falls under n to 1. The fourth example, the set of ordered pairs shown there is a relation, not a function, because the element 0 maps to 2 different outputs. 0 maps to 1 and 0 maps to 0. So this is actually a 1 to 2, violating the n to 1 requirement. Now write out the relation is less than or equal to on the Boolean domain. The Boolean domain only has 2 numbers in it, so there are 3 ordered pairs in the result set. So 0 is equal to 0, so it's less than equal to 0. 0 is less than 1, so that is correct as well. That's another ordered pair in our result. And 1 is equal to 1. So each of these 3, these are the only 3 options on the Boolean domain that satisfy the less than or equal to relation. What n-ary relation is the binary operation plus? So the question is, what is the dimensionality of the Cartesian product? So it turns out a n-ary binary operation is a ternary relation. Remember, binary operation takes 2 inputs and produces a single output. So it's a subset of the Cartesian triple product because the 2 inputs mapping to 1 output results in a nested ordered pair that has a total of 3 elements in it coming from the Cartesian triple product of sets. In these questions we review properties of operations, and in the following consider binary operations on the real numbers, specifically subtraction, addition, and multiplication, which map each are binary operations that map ordered pairs in R squared back to a single real number. And question 1 is, does the subtraction operation commute? If not, show an example that it doesn't. 2, does addition distribute over multiplication? And the other part of this question is, does multiplication distribute over addition? If no, give an example that it doesn't work. And the last question here, 3, if in parentheses a plus b then plus c is equal to a plus in parentheses b plus c, in other words, if we do the addition of a and b first and then add c over, we add b and c first and then add a, if this is the same answer, if this gives you the same answer, what property is the operation said to have? Moving on to the answers, does the subtraction operation commute? No, it does not. We can show by a simple example that it doesn't. Remember, the subtraction operation is a binary operation. It takes a left and right hand side input, and commuting means that we can swap those inputs and get the same answer. And it's not the case here. A simple example here shows 1 minus 2 is not the same as 2 minus 1. Right? So we swap the left and right hand inputs to the subtraction operation. We're not getting the same answer. Question 2, does addition distribute over multiplication? The answer is also no. And we have a simple example here. So 1 plus, in parentheses, 2 times 4. Remember, when you distribute, you open the bracket. So if we try to do that with the addition, we end up with, in parentheses, 1 plus 2 times, in parentheses, 1 plus 4. And that is not the same thing as 1 plus 2 times 4. So we see again that this doesn't work. The other way around, however, it does work. So multiplication does distribute over addition. So addition does not distribute over multiplication, but the other way around does work. Now, the last property, the question was, what property does an operation have? In this case, the addition operation. If a plus b, in parentheses, plus c is the same as a plus, in parentheses, b plus c. In other words, we did the b plus c first on the right hand side, or we did a plus b first on the left hand side. If this holds true, then that operation is said to have the associative property. In this slide, we just ask to review some basic Boolean operations. So if a equals the Boolean element 1 and b equals the Boolean element 0, what is not a, what is a and b, what is not a or b, and what is a or not b? And the answers here, the first one was what is not a, and a was 1 and b was 0. So not a is not 1, so that's 0 or false. The second one, a and b, is in this case 1 and 0. And 1 and 0, remember, and requires truth on both sides, so it requires 1 on both sides, which is not the case, so we will get 0, a and b, 0, or 1 and 0 equals 0. Not a or b, remember the or operation requires truth on either side, either the one or the other side, so not a or b, a being 1, so not a is 0. And remember, unary negation is done first. So we have 0 or 0, and there's not truth on either side. So that's 0. And the last one, a or not b. Not b here is 1, so we have 1 or 1. And or requires truth on either side, so this is certainly true, or 1. So the last question, the answer is 1.